Now we're doing freeCodeCamp, scientific computing with Python beta, learn algorithm design by building a shortest path algorithm, step 31. So just to let you know, in the second half, I've completed it, but I still don't even really know what's going on at the end. So I'm going to try to explain it the best I can, but this one is definitely, you know, it's hard to explain, right? So let's go. So now we're going to call our function passing myGraph and a as the arguments. Okay. So we'll call the function down here. We'll say shortest path. Let's just grab this right here and change it up a little bit. Not like that, though. All right. Not like that either. Let's bring this back. And let's say my graph. So let's put my in front of graph. My underscore graph. And then we'll put a right here. So we'll do what are the single quotes, capital A like that, right? So now we can see we've got this thing going on right here. Where we got all the unvisited nodes right here. And then the distances that we haven't calculated yet, right? So let's check the code. Looks good, and submit it. All right, now we're on to step 32. So all the distances in distances are set to infinite. Yes, except for our starting node. Also true. The unvisited list contains all the nodes in our graph. Yes, that's also true. But actually, we don't need that for loop to achieve this result. So now we're going to remove the for loop and its entire body. Okay, so everything we just did here, didn't even need it, so whatever. All right, so let's check the code. Come on now. We're going to remove our for loop with its entire body. For loop with, don't get rid of the print, right? So this stuff right here. See ya. Check the code, looks good, and submit it. All right, now on to step 33. So the list type constructor enables us to build a list from an iterable. We're going to modify the assignment of our unvisited variable to use the list constructor and pass graph as the iterable. All right, so we'll modify the assignment of unvisited to that. So we'll do list right here, and we're going to pass graph into it. So we're passing the graph parameter in there, and we can see it makes the list of these keys right here. All right, so there we go. Let's check the code. Looks good, and submit it. All right, now we're on to step 34. So with a dictionary comprehension, we can create a dictionary starting from an existing dictionary, right? So we've got the example code, we've got the key, val, and then we say for key in dictionary, okay? In the example above, val is the value that key will have in the new dictionary. So this is the value that's going to be whatever the key is targeting or associated with. Let's say that. And the dictionary is the existing dictionary. Let's bring this down. So it's going to be val is the value that key. Yeah, of course. So yeah, that's basically what's going on there. So we want to keep track of the paths between the starting node and each other node. Okay. After the distance variable, we're going to create a paths variable and assign it a dictionary with all the keys from graph. We'll assign an empty list to each key and use a dictionary comprehension to build our dictionary. Okay. Yeah, this is where it starts getting a little much. Not gonna lie. So after the dictionary is variable, so after the distance is variable, this here, we're going to create a paths variable. All right, so let's do that to start with. We'll say, let's bring this back, paths. And we're going to assign it a dictionary with all the keys from graph. So we'll say equals. And now we're going to do a dictionary, and we'll have all the keys from graph. All the keys from graph. So we'll say key val for key in graph. No, and so it doesn't work like that. Val is not defined. What is defined? Was it node? No. Key val. All right, let's try this again. Let's look at it. After the distance variable, we're going to create a paths variable and assign it a dictionary with all the keys from graph. We'll assign an empty list to each key and use a dictionary comprehension to build our dictionary. Okay, so key. Okay, so it says assign an empty list. All right, so let's get rid of this val. Anyway, let's get rid of this val and put an empty list right there. My bad. So yeah, now we've got this thing. It looks like it might be working now. Let's check the code. Looks good, and submit it. All right. And when they wanted it to be called node, of course they did. Anyway, so now we're on to step 35. So dictionary comprehensions support conditional if-else syntax too. Okay. So we've got this example code: key val1 if condition else, val2 for key in dictionary. Okay, so this value 1, if the condition is true, else we'll put value 2 for the key in the dictionary. Okay, so in the example 1, dictionary is the existing dictionary. When condition evaluates to true, key will have the value of 1. So instead of like a JavaScript ternary where it has the condition in the front, and then if it's, you know, well, let's do a JavaScript. So if that was JavaScript, it would be like condition question mark val1 or else val2. All right. So that's basically what it is. This is going in the front. The condition is going after an if, and then instead of this thing right here, we're having else val2, right? So that's basically what's going on right there. So in the example above, dictionary, I'm going to go through this again. Dictionary is the existing dictionary. So that's the existing dictionary. When condition evaluates to true, when this is true, key will have the value of 1. So the key will be this if this is true, and if not, the value for this key will be this, okay? So that's basically what that says. So we're going to use a dictionary comprehension, to create a dictionary based on graph and assign it to the distances variable. We'll give the key a value of 0 if the node is equal to the starting node or infinite otherwise. We'll use float inf to achieve the latter. So yeah, you can see why I got a little frustrated and had to do this before recording. All right. So yeah, let's do that. So we're going to assign it to the distances. So we've already got this set up. Let's give the key, we'll say key equals 0 if node is equal to starting node. If node, no. Key 0 if node is equal to starting node, all right? Else it will be inf, all right? But this inf is going to be wrapped up in parentheses, and we're going to put a float in front of it. Float, okay? And then for key in graph. So let's do that for key in graph, all right? So it's this key in graph. No, node is not defined. Oh yeah, we got to call it node. Node. Boom, there we go. Okay, so that should take care of it. We do have the thing that we had earlier, however many lessons ago. So I guess it's good now. Let's check the code. Looks good, and submit it. All right, now on to step 36. Pardon me. Since the algorithm begins its assessment from the starting node after creating the paths dictionary, we're going to need to add the starting node to its own list in the paths dictionary. We're going to use the append method to append start to the paths start list. I mean, so many words, you know what I'm saying? It's like, could you take some of those millions and maybe make some, animations to, help out what you're talking about, because I don't even know what's going on. Let me try to read this again and try to get us to understand it. Maybe you guys understand it already and I'm just wasting my time. Let me do it anyway. Since the algorithm begins its assessment from the starting node, from here, I guess, after creating the paths dictionary, we need to add the string node to its own list. I don't know what this means. I don't know what this means at all. We're going to use the append method to append start to the paths start list. Okay. So let's just do what they tell us. Maybe it'll click later. Paths start dot append, and then we'll put start in there. Okay, didn't do anything here. What would this basically do though? Paths start. Paths at start. Okay. What are we pushing in here? A. So the A is the start. Okay. So paths at A. Paths at A. Paths equals node for node in graph. Oh, yeah. Okay. Paths equals node for node empty array, empty list for node in graph. So we're okay. So yeah, I can't visualize this. I can't visualize what's happening. That's the thing. I cannot visualize this because there's nothing to visualize. You know what I'm saying? Paths node for node in graph. So it's going to be a pin start. So we're going to put A into this, I guess. All right. So maybe there's going to be A in this for node in graph. For this one, it's going to be A. I don't know. I can't visualize this. I just don't have what it takes to visualize what's going on right now. And make a video. That's what I'm trying to say. While I'm making a video, what am I supposed to do? Learn this beforehand, like for like 5, the 10, 20 views, the 30 views, 100 views that this video gets. What am I supposed to do? You know what I'm saying? These guys don't make it easy on a man. Check the code, looks good, submit it. We're just going to the next one, guys. Because I can't visualize this. I cannot. What am I supposed to do? Like, am I supposed to take 30 minutes, 40 minutes, an hour, 2 hours to go to visualize this thing for like this video? I already know this video is going to be up for like 2 years and it's going to have like 1,000 views. What is that? It's like $1. It's like $2. Anyway, let's go. But I'm trying to learn it too, so I should be visualizing it. God, this is bullshit. Oh my God, these people that are getting paid. Whatever. Step 37. So now we're going to add it. The in paths. Oh my God. We're going to add this at the end of the F string passed to the print call so that it prints the paths variable too. I'm about to explode. All right, so let's add this to the end of the F string. So we'll say this, paths, and then we'll have a thing like that, and we'll say inside of here, paths. Let's just grab paths right here. Oh, man. There we go, and submit it. I'm telling you, they don't care about us. They just want to get their money. And they just want to go pay their bills and live in San Francisco like a bunch of we know who lives in San Francisco. There's a reason they've got a teddy bear for its symbol, guys. Look it up. If you know, you know. So here's step 38. So our function is going to explore all the nodes connected to the starting node. Okay. Okay. It will calculate the shortest paths for all of them. Okay. Then it will remove the starting node from the unvisited nodes. We're just going to have to get through this and just go over to freaking free code. We just have to go over to Code Wars and just say, okay, we did it. So next, the closest neighbor node will be visited and the process will be repeated until all nodes are visited. So from now on, we are going to work on the main loop that explores the nodes in the graph. To avoid issues with running an infinite loop during the algorithm development, we're going to turn our function call into a comment. Do you know what this stuff means? I don't. I swear they think that they are teaching us, but all they're doing is just saying words to people that don't understand what the words mean. I know this because I've got a friend who works in a machine shop and he's always telling me about the nuts and bolts of this. And I'm just like, bro, I don't know anything about this. You're saying things that I don't understand, whatever. Check the code, looks good, and submit it. The thing is, he's not getting paid to tell me all that BS. These guys are getting paychecks. Step 39. Before the print call, we're going to create a while loop that runs while unvisited is not empty. We're going to use the pass keyword to fill the loop body. Okay, before the print call, before this, we're going to create a while loop. All right, so let's do that. Let's drop this down. While, let's drop it down 2. How about that? While unvisited is not empty. So while unvisited, visited, all right? Because this is going to be a list. So, what? Okay, and then we'll do this, and then we'll put pass in here. So while unvisited exists, we're going to do something, right? So let's check the code. Looks good, and submit it. All right, now we're on to step 40. So inside the while loop, the first thing to do is define the current node to visit. Pardon me. For that, we can use the min function. It returns the smallest item from the iterable passed as an argument. And they'll totally explain very clearly things we've gone over like 15 times in the past. You know what I'm saying? That's the kind of guys we're dealing with. So we're going to remove pass, then create a variable called a current and assign it min unvisited. Okay. So we'll say current equals min unvisited, like that. That should be it. Let's check the code. Looks good, and submit it. All right, now we're on to step 41. So min also takes a keyword only argument. Passing a function as an additional argument to min, we can modify the way the list items are compared. What does that mean? The result of the line we've just written in the previous step is the node that comes first in alphabetical order. So this is the node that comes first in alphabetical order. So if it's A, it's A. Are we in the middle of a for loop? Yeah, no, we're not. We're just in a while. So if it's A, it's A. If it's B, it's, I don't know. I don't know what that means. The result of the line we've just written in the previous step is the node that comes first in alphabetical order. So A, okay. Instead, we want to select the unvisited node having the smallest distance from the starting node. Okay, so that makes sense, I guess. So we would want D, I guess. And then from B, we would want A. Okay, so we'll find that. Okay, so we're going to pass key equals distances dot get as the second argument in our min call. Okay, as the second argument in our min call. In this way, the comparison will take place depending on the value each unvisited list item has inside the distances dictionary. Okay, so we're going to find the minimum of these two things. Okay, so this one would be D, this one would be A, this one would be B, and this one would be A. Okay, so let's do that. So to do that, pass keys equals distances dot get as the second argument. So we'll say we're going to say key equals distances dot get. All right, which we have not gone over, this get thing. Get Python, dot get Python. Let's put a dot get Python. Boom. Let's come over here to Geeks for Geeks right here. And let's look. All right, push bar break. Let's look. Pardon me. So this isn't, I don't even know if this is the dot get because this has parameters in it, whilst this one does not. Okay, anyway, let's just look. So we're going to pass key equals distances dot get as the second argument in our min call. In this way, the comparison will take place depending on the value each unvisited list item has inside the distances dictionary. Min of the unvisited, and then key equals distances dot get. What the? Let's go look at the min thing. Min Python. Boom. All right. Where's Geeks for Geeks? Boom. Push pause. All right. Python min function returns the smallest of the values. Okay, we know that. Parameters. Okay, key optional. A function to customize the sort order. How to use the min Python. That's what we're looking for. No. All right, here we go. In this example, we're using min to find the minimum element in a dictionary. Okay, so print. No, that's not good either, actually. Okay, so they don't even have any freaking examples. Whatever, we'll just try to get it through this. All right, I think that's what they want. Check the code looks good and submit it. Whatever. All right, step 42. After the current variable assignment, we're going to create a for loop to iterate over the tuples in the graph current list. We will need 2 iterating variables for that. We'll remember to use pass to fill the loop body. So after the current variable, after this, we're going to create a for loop. This is garbage, by the way. Okay, this is why you cannot get smart using this thing. This is only to open our eyes. We have to go to Code Wars after this because there's no way, there's absolutely no way to do anything productive with this worthless information. Okay, with this hand holding. Okay, here now, turn left, turn right, turn left, turn right, turn left, turn right. Okay, you're there. How did I get here? I don't remember. I don't have a brain that has an actual computer in it, bro. All right, so let's keep going. So after the current variable assignment, create a for. I know this because I used to drive Uber a lot. You cannot remember. You have to go to a place like 5, 6, 7 times to actually remember where a place is, or you just forget. It's just how humans are. All right, so we're going to create a for loop to iterate over the tuples in the graph current list. We will need 2 iterating variables for that. We're going to remember to use pass to fill the loop body. Okay, so we did for to iterate over the tuples in the graph current list. For tuple in graph current, we will need 2 iterating variables for that. Okay, let's do I and j. I, comma, j. All right. Remember to use pass for the body. Okay, let's come down here and say pass. Okay, so yeah, that's how we do that. I think okay, looks good, and submit it. All right, now we're on to step 43. So now we're going to create an if statement to check if the distance of the neighbor node, the second item in the process tuple, plus the distance of current is less than the currently known distance of the neighbor node, the first item in the process tuple. We're going to use the pass keyword to temporarily, fill the body of the if. Okay, so we're doing an if here, but I don't remember what it said. If. the distance of the neighbor node, the second item in the process tuple. So j, if j plus the distance of current, wait, did we call it j or did they call it something else? Distance, okay. All right, if distance plus the distance of the current is less than, okay, plus distance current, all right, is less than the currently known distance of the neighbor node. Is less than the currently known distance of the neighbor node. Is less than known. Node, and it's the current one, so we'll put current. Okay. Then we'll do pass. So now we're going to say pass. All right. So if distance plus distance current, so what's distance? Distance, all right, graph current. Current is either going to be the smaller of these two, is going to be the smaller of these two, right? So let's say, so if distance plus distance at current, so 1 plus, so what's the distance though? For distance, graph current. So this is graph, this is current, distance. All right, I don't know what's going on. Check the code. Nope. I didn't even know what was going on here. We should have an if statement. Oh yeah, what? To check if distance plus distances, my bad, current is less than distances node. Okay. Distances node. Yep, that's what we're dealing with, guys. Check the code, looks good, and submit it. Distance plus distance is distance. Graph current. This would be the graph at current. So the first one would be the distance, the node. And then the second, oh, is this the node? And this is the distance, right? I don't know. All right, so whatever. So when the condition of our new if is true, a shorter path to the neighbor node has been found. Inside our new if block, we're going to delete pass and reassign the neighbor node distance to the sum of the neighbor node distance plus the distance of current. These guys, I'm about to blow a fuse. Honestly. When the condition of our new if is true, okay, a shorter path to the neighbor node has been found, okay? So inside our new if block, inside of here, we'll delete pass. Let's do that first. And reassign the neighbor node distance. Neighbor node distance, what does that mean? Distance is at node. Is that what you want? Is that what it is? We'll see. To the sum of the neighbor node distance plus the distance of current. Plus the sum of the neighbor node distance plus the distance of current. Node, I don't know. Node plus let's say distance is current. This is just a guess, honestly. What am I supposed to do here? What are we supposed to do here? All right. Reassign the neighbor node, say equals trash. We should assign distances plus distant current to distances. No, okay. We get this and this. All right. Check the code, looks good, and submit it. That's what we're dealing with, guys. We can't. Can I be a full stack engineer after taking freeCodeCamp? Of course you can't. Of course you can't. There's no possible way. How could you possibly think you could get anything productive out of this thing other than being somewhat familiar with this? If there's a person that can get a job, it's because his dad is the boss. That's the only way. All right, step 45. Once the distance to a node is set inside the distances dictionary, we need to keep track of the path to that node too. If the distance for the node in the process tuple has been updated, the last item in its path is the node itself. What kind of sentence is that, bro? I don't know. I don't know what this says. Do I have a learning disability? Once the distance to a node is set inside the distances dictionary, we need to keep track of the path to that node too. So we're keeping track of the path to the node. What does that mean? I don't know. If the distance for the node in the process tuple has been updated, the last item in its path is the node itself. So if the distance for the node in the process tuple has been updated, if the distance for the node in the process tuple has been updated, the process tuple, what is this? Has been updated. The last item in the path is the node itself. Inside our conditional, we're going to nest another if statement that triggers when the last element of paths at node is equal to node. I'm going to read it again, and I'm still not going to understand it. Inside our conditional, we're going to nest another if statement inside the conditional. The conditional. Is that this? I've done this before. It is this. The only reason I know is because I did it before and I had to cheat to get the answer then. We're going to nest another if statement that triggers when the last element of paths dot node. So paths at node, the last element is -1. All right. Is double equals node. And then we're going to say pass here. We're also going to say if in front of it. If. And then we'll tab this over. Check the code looks good and submit it. All right, now we're on step 46. So now we're going to remove paths and assign paths at current to paths at node. Okay. So paths at node now equals paths at current. What's going on? What's going on? What is going on here? Check the code looks good and submit it. The extend method allows us to add elements from an iterable to the end of a list. Okay. So like we've got this my list. We've got a couple of trees here. And then we've got tree list and some more trees. So my list dot extend this list right here. So this dot extend this will make a bigger list with all 5 in there. Okay. So yeah, that's how that goes. It's kind of like the same as doing in JavaScript, my list dot push, and then we would say we would say tree list, and it would put this at the end of this. All right, same thing. So we're going to create an else clause and use the extend method to add the current node path, to the neighbor node path. Okay. So we'll say down here else, and then we will say the extend method to add the current node path to the neighbor node path. So I think that this is the neighbor node dot extend, and this is the current node path. Check it. Looks good and submit it. I don't know what's going on. Finally, below the else clause, we're going to append the neighbor node to its path. Below this, and the thing is, it's like we're doing all this complete garbage and nothing's happening over here. Nothing. There's nothing. Nothing's going on. We can't see it in real time. We're just like, hey, trust me, bro. Trust me. It'll get done, guys. It'll get done. Just trust me. Like, get out of here. Get out of here. you know, but whatever. I swear and they're getting paychecks. Don't forget, they're getting paid to do this. Fine. Finally, below the else clause, we're going to append the neighbor node to its path. All right. So below the else clause. So inside of this if right here, we're going to append the neighbor node to its path. So this is the neighbor node to its path. No, this is the path of the neighbor node. All right, so let's say paths.node.append. Say dot append, and we're going to append the neighbor node to its path. All right, so let's put node. Check the code. All right, looks good. And yeah, the only reason I did that is because I know that this is the neighbor node path from the last ones. So it's got to be, this has to be the neighbor node itself. That's the only way I knew. It wasn't because I understood what was going on. It's because of context clues in the poorly written instructions. All right. No, there's no comprehension in my brain right now. None at all. None at all. And you're watching the video for it. So what's that doing for you? I don't know, man. Thanks for watching. Step 49. The remove method removes a list from the first matching element that is passed as the argument. Okay. I guess it's misery loves company. That's the only reason. If you've gotten this far, it's because misery loves company. And you know that I'm just as pissed off as you are. All right, so let's do it again. The remove method removes from a list the first matching element that is passed as the argument. I believe it. My list, large 1, true 1. So my list.remove 1 would remove this 1 because it's the first matching element that's passed as the argument. So when we do print my list, and the output would be large true 1 because this one is gone. Okay. Pardon me. So we're going to terminate the while loop by removing the current node from the unvisited list. We'll pay attention to the indentation. So we need to be here because we're terminating the while loop. So we'll back it up 2 times to right there. Good. So by removing the current node from the unvisited list. Okay. So we will say unvisited.remove, and then we'll do the current node from the unvisited list. Okay, so let's say node at current. No, we're not inside of this for loop anymore. Let's just say current. Let's see what happens. Current. Check the code. Looks good. There we go. And submit it. It was a guess. I still don't know what's going on. Step 50. If we try to uncomment our function call, it won't work. Okay. If we have, we have a couple bugs to fix. The first one could have fooled me. I mean, look, how do we know we have bugs if we can't even see the thing, right? First one happens to be in the nested if. In the nested if we are trying to access. The first one happens because in the nested if, we are trying to access an element that might not exist in our paths node list. Oh, okay. I don't know what that means. So we need to be sure that the paths node is not empty before accessing paths at node -1. An additional condition to our nested if statement. We're going to add an additional condition to our nested if statement to ensure that paths at node is non-empty before accessing paths at node at -1. Okay, cool. An additional condition. So we're here to ensure that paths at node is not empty before doing this. All right, so before we check this, we need to make sure that this exists. All right, so we'll grab paths at node here. No, like this. No, like this. How about this? Copy that, and in front of this, we will say paths at node space and. Okay. I don't know if we went over and, but instead of doing and, like in JavaScript, we just say and it's the same thing. All right. All right. Let's get out of this. It doesn't matter. Check the code. Looks good and submit it. All right. Now on to step 51. So now we're going to uncomment our function call. Oh, I wish. Anyway, whatever. All right. So now we've got this going on, which is something. Okay. Which is something. This stuff right here is this right here. While unvisited, while unvisited. Look, I'm not going to, how long would it take for me to figure this stuff out? I mean, I should figure it out, but at the same time, I haven't put out a video in 2 days because I was just trying to figure out how to get through this thing. Check the code, looks good, and submit it. I should go through it. I should go through it and tell you how to do it. I should, that's for sure. But, you know, how long is that going to take? Why don't we just figure it all out in Code Wars? That's the way I feel. And then come back later, maybe? I don't know. Step 52. The other bug is subtle. When a shorter distance is found for a neighbor node, paths at current gets assigned to the neighbor node path. Paths at node. Okay. This means both variables point to the same list. Since lists are mutable, when we append the neighbor node to its path, both paths at node and paths at current are modified because they are the same list. So this list and this list are apparently the same. Okay. This results in wrong paths, although the distances are correct. Okay. We can fix that bug by assigning a copy of paths at current to the neighbor node path. For that, we can use the slice syntax. Okay? And here's the slice syntax. It's really pointless to go over to Geeks for this because it doesn't explain it any better. But yeah, we're going to do something like this. My list, and then inside of here, we'll do this right here. This apparently is slice syntax. So where my list is the copy, where my list is the list we want to copy. We're going to modify the existing paths at node equals paths at current assignment inside our if block by slicing paths at current. Okay. So yeah, we'll just come down here, modify the existing paths, and then we'll say paths at current. We're going to slice it by just doing this right here. And we can see that something does happen. Okay, so the C got taken off of this one. Nothing happened to this one. See anything happen to this one? And nothing happened to this one. So the C got taken off of this one. And that's what happened. Okay. Check the code. Looks good. And submit it. All right. So now we're on to step 53. The algorithm is complete, but we can improve the output. Okay. Could have fooled me. Also, we can provide the function with an additional argument to return only the path between two nodes. We're going to add target as the third parameter to our function declaration and give it the default value of an empty string. All right. Another little aside. The only thing I can imagine is that later, at some point when we're actually building actual stuff for ourselves, we'll get to a point to where this stuff is necessary, or we're going to have to write a million freaking lines of code. And then we're just like, oh, that makes sense. After we've been doing this a long time, this stuff comes around and we're like, oh, okay, this makes a lot of sense. Oh, it makes perfect sense. And then some noob comes up to us and says, how do we do this? And we say, oh, here's the freeCodeCamp version. And they're like, what? You know what I'm saying? Hopefully that makes sense. Let's go to 53. The algorithm is complete, but we can improve the output. Okay. We can provide the function with an additional argument to return only the path between two nodes. What? So we're going to add target as the third parameter to our function declaration and give it the default value of an empty string. So we'll do target right here. And give it the default value of an empty string equals empty string. Okay, we know how to do that. Did anything happen is the question. Nope, nothing happened. Check the code, looks good, and submit it. All right, now we're on to step 54. So Python provides a concise way to write if-else conditionals by using a ternary syntax, all right? The ternary syntax. So it's just like that one before when we put it in the what is it, the for loop. So where was it? Where was it? I know we did that before. You remember doing it before, right? Where is it? Node Z. Okay, it's just like this right here, remember? It's exactly like this right here. So we're going to have val1 if condition else val2. So val1 if condition else val2, right? So it's just like this thing. In fact, it's the exact same thing. The expression above evaluates to value 1 if the condition is true, or otherwise to value 2, right? So we're going to delete our print call and create a variable called targets to print after a while loop, and we'll use the ternary syntax to assign it target when target is truthy and graph if otherwise. Okay, so let's get rid of this. We'll say targets to print, targets to print equals, and then we will assign it target when target is truthy. All right, so let's wrap this in a set of brackets. If target else graph. All right, so that's basically what it's saying to do. Check the code, looks good, and submit it. All right, now we're on to step 55. So now we're going to create a for loop to iterate over targets to print. Okay. And print the following f string, this stuff right here. Right? We're just going to copy paste this. Actually, no, we should type it out so we know what we did. So we'll create a for loop to iterate over targets to print. So for target in targets to print, we're going to print the following string. Well, it'll be an f string, and inside of here we'll do /in. Then we'll have a what is that thing called? Embedded expression hyphen another embedded expression space distance colon space another embedded expression. And then another /in path. And then we'll do another embedded expression after that. All right. So this first one's going to have start in it. So we'll just take, is there a start around here? We'll just type start. Why not? So we'll say start in here. And then node, we got a bunch of nodes up here. We can just take that one. Put node here. All right. So this one right here, I should say, is going to be node again. No, it's going to be distances at node. So we'll use this distances at node right here. Put it right here. And then we'll put here this stuff. So we'll have a set of double quotes. Inside of the double quotes, we'll say space. We'll have a hyphen, a right pointing angle bracket. And then we'll say dot join. And we'll say paths at node. So we got paths at node right here. Let's take that. I'm not saying it's the only reason I'm doing this is because it's not like it's hard to type, but it's easier to avoid those dumb what are those things called? Typos, that'll result in error if we just do it that way, right? So now we've got this going on right here. So we've got AD distance 1. So it would be start to node. So A to D, distance, and the distance is a node right here. And then it goes and drops to another line. It says path, and then it says join paths. So we're going to have paths at node. Paths at node is going to be joined by this thing right here. So it's going to say A, this thing, D, like that. Just like on all 4 of these. Okay. So that's basically what's going on there. Let's check the code. No. Okay. Oh, it wants us to use node. Even though it works with target, they want to get in our faces about it not saying node. Or actually, no, it should be node because this looks completely different than this. Okay. Well, my bad. I guess it's because target's already been declared. I guess since target, where did we declare target? I don't know. So we're using node and not target, and it does this instead. So it has A, because distance is 0, A to B to C, and then A to D. Gotcha. Check it. Looks good. And submit it. All right. Now we're on to step 56. So now it's better, but we don't want to print the details about the starting node. Okay. This one, I guess. Before the print call, we're going to add an if statement to execute when node is equal to start and use the continue keyword to go to the next loop iteration. So yeah, if node double equals start, like it's at A to A on the first one. Let's go back here. So like it's A to A here. So if node equals start, what we want to do is say continue. All right. So it'll go on. It will skip doing this because it says continue. It'll just skip and go to the next one, right? To the next iteration. It checks it. It's not good. It's not node equals start. So it does this, etc., right? And we can see A to A is gone now. Check the code. Looks good. And submit it. This is like the only part I understand. So step 57. Finally, at the very end of our function, we're going to return distances, comma, path. So we'll come down here and we'll say return. Oops, what is that? We'll say return distances, comma, paths. All right. Did that do anything? It doesn't look like it. Check the code. Looks good. And submit it. All right. So here's this. So now we're going to test our function with another graph. We'll change my graph to the following graph. We're definitely copy and pasting this. So let's copy from here to here. Take it from here to here. And paste. Let's try that again, but this time for real. Do that. Come down here. Paste. All right. So now we've got all this stuff. Distance is 4. Distance is 3. AC, distance 4, ACD. And these are all the shortest paths according to our code right here. And this is all the code. This is what is this 34 minus 9. So what, like 23 lines of code? But this stuff right here, we're going to have to, personally, each one of us needs to look through this and figure out the whole thing, figure out what's going on, because maybe this thing's important. And that's not a lot of lines of code. You know what I'm saying? So that should be good. Let's check the code. Looks good. And submit it. So step 59, as a final step, we're going to modify our function call passing f as the third argument to print only the path from A to F. And with that, the shortest path algorithm is complete. So my graph A. So these are all of the paths with A. And so A to F like that. Okay. And so this is how the shortest path works right here. But like I said in the last step, each one of us is going to have to go through this and figure it out, because I'm not coming back to this. I'm not coming back. At some point, we will probably experience this in Code Wars, and maybe we'll figure it out then, but not coming back. Looks good, and submit it. All right, so that's the end of that. So now we're going to go over to the learn recursion by solving the Tower of Hanoi puzzle. Recursion, everybody's favorite. So we're going to do that next time. We're going to start that up on Sunday. Other than that, there we go. And we'll see you next time.